Okay, so thank you very much. So let me start by thanking the organizers for this workshop and also for being able to fit us into the schedule. So us, that's Quentin Bonfoy, Gauthier Durieux, Christophe Grosjean, and Camila Machado. And I would like to report on our work that's called The Seeds of Effective Field Theory Double Copy. And we believe that it fits very well within the title of this program because one of our research goals was to bridge together two recent proposals for the double copy in the context of effective field theories. And that's exactly what I would like to report on. But let's start very basically looking at the double copy as a map from two theories into a third theory. And here I will only work at tree level. So you should ask yourself questions like we all do, what is this map and which theories can participate? And on a practical level, you can answer this by in two different ways, or at least two different ways. One of them being the KOT way, which is saying that, which has a KOT product. This is named after Kawai, Llewellyn, and Tai. And it says that the theories that participate are the theories that satisfy certain consistency relations, which are called the Kleist-Kalf and the Bernd-Carrasco-Johansson relations. And then there's another way of phrasing the double copy, which is the color kinematics way. And the theories that participate are the theories that satisfy this color kinematics duality. And on the renormalizable level, these maps and the theories that participate are exactly the same. These maps are equivalent. And using this map, you can, as we saw yesterday in the last two talks, you can form a whole web of connections between different theories. And one question that I would like to ask is, what happens inside this map, or what happens if you look at one specific relation between theories, if you allow for small perturbations in the sense of turning on one higher dimensional operators that is suppressed by some high energy scale lambda. So if you work at low energies, this suppression by high energy scale lambda ensures that this is a small correction in your amplitudes. So if you allow for such corrections, then you should really be looking at this map as a map between effective field theories, where an effective field theory is at lowest order a renormalizable theory, and to it you add everything you can think of, higher dimensional operators, and they are all suppressed by some high energy scale lambda. And then there are free parameters, AI, BI, which you can freely choose depending on experiments or on theoretical properties you want. So one thing to note is that the traditional way of doing double copy, as I said, in this KOT or color kinematics way, also works for effective field theories, meaning there are some EFTs that can be double copied for particular choices of these parameters. But since in effective field theory context, we allow for higher dimensional operators, we have more freedom with these parameters, you may ask, can we generalize the idea of the double copy? And in fact, previous literature has done this. And in the two different languages, out of those came two different ways of generalizing the double copy. And these have been generalized independently. And so you might ask, is this generalization in the same direction because the starting point is the same? These two ways of doing double copy are the same for renormalizable in the non-generalized sense. Or maybe the generalizations, do they move into different directions? And one reason why this is an interesting question is if you look at going to loop level, this in the color kinematics case there's a prescription to do it, but it's less clear in the KOT way. So it's really an interesting question to note whether these generalizations are the same or not in the color kinematics and KOT way. So let's have a look at this previous literature that has proposed these generalizations. In half a talk, I'm not able to describe what is worth two full talks. And in fact, I should also not do it because this program has these two topics covered. So for one of them, see a talk tomorrow by Paranchapi, and also see the talk yesterday by Carrasco, where these ideas are discussed. But here I will just select out the elements that are important for me. And so for a fair description and a complete description, see these other talks and these works. But for me, let me give an idea of what this KOT double copy is. In the KOT double copy, what you consider is, so we've also seen this yesterday in some degree, but it's good for some repetition. The way of taking out color amplitudes is by taking out independent color factors in the form of traces of your generators. And what is left is then your ordered amplitudes. And in particular, doing this for a special theory called the bi-adjoint scalar, which is a scalar theory with two color groups. you end up with matrices of ordered amplitudes, because now you can take out two independent traces. Right, and so this matrix has indices depending on which ordering of the trace you've taken out. This matrix is really central in this KOT formalism of doing double copy, because it defines, first of all, consistency relation on the theories that may participate, using this, what is called the KOT kernel, which is an inverse of a submatrix of this matrix. So it defines consistency relations. These are the KK and BCJ relations. And it also defines how to perform your product between two amplitudes. So taking this matrix really as the key object in this language, how to generalize this, or how to generalize this in the context of effective field theory. So how to include higher derivative corrections. That is by including higher derivative corrections inside this matrix. So that is by obtaining a bijoint scalar effective field theory with higher derivative corrections. And not all higher derivative corrections result in a good matrix that defines a proper double copy product. So only particular corrections are allowed, which preserve the right properties of the bijoint scalar. And these are discussed in detail in this work, and hopefully we'll see it also tomorrow. The upshot that I want to take is that doing this, so adding corrections to your matrix, allows for more effective field theory amplitudes to participate in the double copy. All right, so on the other hand, we have the language of the color kinematics double copy. And there we organize amplitudes differently. We organize, as we saw also before, in terms of trivalent graphs. And then we split off the color information in terms of these numerators. So we have a numerator consisting of color and a numerator consisting of kinematic information. And the color numerator satisfies relations called the Jacobi relations coming from the Lie algebra. And the fact of this color kinematics duality is that these kinematic numerators satisfy the same relations. And you can therefore form a double copy by combining two of these numerators in the way shown here. So I'll just continue, I don't know. Okay. So what the thing to note here is that there's a distinction between the two numerators. One of them contains only color and one of them contains only kinematics. So how to generalize this notion, allowing for high derivative corrections? That is by taking one numerator that can consist of both color and kinematics. So that's the idea of this, of introducing generalized numerators. They can be function of color and kinematics at the same time. And this then also allows for more amplitudes to participate in your double copy. Right. So taking this as a starting point, what I want to do is by introducing some simpler objects, which we call seeds, I want to make these two different frameworks talk to each other and also gain some insight in them. So what is the idea of seeds? So for basic color, what we know is that one entry of this numerator, so one color factor, can be decomposed in the traces of the generators. And these traces are really simple in the sense that if you look at them as a function of ABCD, then it's just a cyclic function in ABCD, and the different traces, so the different permutations, are linearly independent. That is in contrast to the numerators, the adjoint numerators, which satisfies these complicated relations, these Jacobi relations. So doing this for all the numerators, you obtain a matrix equation where now we have taken apart, we have a matrix that encodes the Jacobi identities, and we have the traces, which are simple functions. They have one functional form, and they are, the only constraint is that they're cyclically invariant and they are linearly independent. Right, so taking this as a starting point, we are going to do exactly the same for these generalized numerators, which we saw may contain both color and kinematic information. But because they have the same algebraic structure, you can do the same decomposition. So for an adjoint numerator, which can be very complicated with both kinematics and color, and the different permutations need to satisfy linear relations, it can also be taken apart into this matrix that encodes the Jacobi identity. And this is what we call seeds. So these are objects which are cyclically invariant. So they're cyclic in these labels. in these particle labels. Excuse me. And so it's simple to generate these seeds and from them construct adjoint numerators. And I should note that this was also done in the non-generalized case, but for kinematics in previous literature. So we have generalized this notion. Sorry. All right. So what I want to stress here is that the seeds are really simple objects that you don't even need to write down ansatz and bootstrap it, but there's a way to generate the whole seed. So I want to emphasize this by looking at the structure of this, first of the color bases, and then going to kinematics. So the color bases, we know that it splits up in, you can choose either the single traces, or you can choose your bases in terms of the adjoint structures and permutation invariant structures. And this you can do, you can as a sub-step, you can first combine them into combinations that are symmetric on the reversal and anti-symmetric on the reversal. And here, importantly, from these, we have the same matrix as before to obtain the adjoint structures. So the whole space of polynomials now, once we look for seeds, which depend on the Mendel stems, this whole space looks exactly the same. So we have, starting with trace-like functions, which are functions of the Mendel stems, but they have this cyclic property. The whole space splits in the same way, and instead of using your trace-like functions as a basis, you can use your adjoint structures as a basis, or permutation invariant structures, and it's the same matrix here that maps. So just to illustrate that this ring of polynomials here is really can really be fully understood because this constraint is so simple in contrast to the adjoint structures. Let me give you one object that encodes all the information about these polynomials, which is the Hilbert series. So what the Hilbert series does is it counts the number of independent polynomials per degree. So here, this expansion here tells you that upon imposing this constraint, there's one independent polynomial of degree 0, which are just numbers. There's one independent polynomial of degree 1. There are 2 at degree 2, etc. And this resummed form also encodes information about the form of the generators of this polynomial ring. So the whole ring can be generated by a generator of degree 1 and one of degree 2. So this is an interesting object that encodes for you some all-order information. And the only thing actually I want to illustrate with this is that these seeds are so simple and can be really solved for that you understand the whole ring at all orders. In contrast to, although misleadingly, I will also show the Hilbert series for the adjoint structures. At higher orders, I expect that these will be complicated to obtain, but at higher multiplicity, these seeds are just as simple to understand. So you can impose also reversal symmetry and anti-symmetry, and actually there are no solutions if you want reversal anti-symmetry. And you can write down the Hilbert series for the adjoint structures and the permutation invariant structures. And this then tells you how many polynomials are there which satisfy the adjoint structure, so which satisfy the Jacobi identities. All right, so the same you can do at 5 points, actually at any point. It's very useful to note that there's a particular base of Mendel stems that makes these constraints simpler, which is this cyclically invariant basis. So in terms of this basis, the constraint of being a seed, so the constraint of being cyclically invariant is more simple. And then we can also write down the Hilbert series, which look more complicated, but it's just as straightforward to obtain them. And from then you can get the counting of how many independent operators are there that can take part in this double copy. All right. But let's get back to what do we want to use these seeds for? We want to build amplitudes which satisfy color kinematics duality. So for example, for Young-Mills, you can build amplitudes starting from your normal color kinematics dual Young-Mills amplitude. If you want to include higher derivative corrections, one way to do it is to take this color factor and replace it by a generalized color factor. So including higher derivative corrections inside this numerator. The theory that we are also interested in is this bi-adjoint scalar theory, which at lowest order has just numerators consisting of only color, because it has one vertex which has 2 color groups but no kinematic information. So if you want to include higher derivative correction here, just in the same way, we're going to include higher derivative corrections to these numerators by replacing them with generalized numerators. And these are amplitudes which, so because the biadjoint scalar plays such a central role in the KLT formalism, these are amplitudes that we will look at on the next slide, because they will form the bridge towards the KLT description and also the generalized KLT approach. All right, so let's do that. So this amplitude that we saw before can be written in terms of matrix notation first, where we just put all the propagators on the diagonal. And then we have our adjoint numerators, which we now know we can decompose them into our seeds, and this matrix J, which encodes all the Jacobi identities. And then in this gray box here, we have what is called the matrix of ordered amplitudes for the biadjoint scalar, which you can see. But if this were not a generalized seed, but if these were just a single traces, then you have just a biadjoint amplitude, and this then being the matrix of ordered amplitudes because you have taken out two traces. But now it's not just the traces. Now these are generalized because they contain both color and kinematics. So you can further decompose them. You can decompose them in a factor of pure traces and some matrix that encodes all the kinematic information. And now within this red box, this is the generalized, this is the higher order, or these are the higher derivative corrections to the biadjoint matrix of ordered amplitudes. And this is an object that would have been constructed by the bootstrap of the work that we're going to hear about tomorrow. So this is an object that defines through the KK and BCJ relations which theories are allowed to participate in the double copy, and it also defines how to combine two theories and obtain a double copy amplitude. So because we now have this insight in what does it look like, such matrices, such high derivative corrections to these matrices, we can look a little bit further into them. So the matrices themselves look like this, and the single copy amplitudes that are allowed by these matrices have a similar form, except that instead of having one color group, we have here extra kinematics because we have coming from an amplitude with only one color group instead of two. And you can take out the color on the left side or on the right side. But the point is here, it's the same matrix appearing in both cases. So also for the single copy amplitudes. And then double copy amplitudes that you construct in this generalized way have the same matrix appearing as well. So this is gaining some insight in the form of the amplitudes that can participate and the double copy amplitudes that can be reached, finding the seeds appearing. All right. So some conclusions that can be made in this way. So I have not told you all the technical subtleties that are behind this research. So these are not all conclusions from this talk, but partly conclusions from our work that has gone behind it. First of all, is one conclusion from this talk, which is that seeds are straightforwardly generated, and they construct adjoint numerators and KLT kernels. So from these simple objects, we can construct both generalized numerators and these KLT kernels for the KLT double copy. And via seeds, we can map between the color kinematics language and the KLT language. And this shows that also in the generalized way, these two languages are still equivalent. So also all KLT kernels can be generated from generalized seeds. But there's one subtlety. So this is actually coming from this correspondence between these two languages. But there's one subtlety, which is in this correspondence, it is not clear whether the seeds that are required have a what their pole structure is, basically. So the question is, do they have poles in the Mendel stem, or is it enough to consider only seeds that are polynomial in the Mendel stems? Thanks. Up to this, so this subtlety has been fully understood and addressed at 4 points, where we understood that indeed all KLT kernels can be generated with polynomial seeds. At 5 points, however, it is still an open question whether this is enough or whether we need to include poles in the seeds. And this is an important point because if you have poles in your seeds, then you're not guaranteed that the amplitudes you construct with them are physical amplitudes, or perhaps they have non-physical poles. So this is why this is something that needs to be addressed. And that is for future work. So thank you very much for your attention. And of course, if there are any questions, I'll be happy to address them.
Thank you very much for a very interesting talk. Any questions from the audience? Did I miss any? Okay, could I have a quick question? If you could classify, if you could figure out what locality properties these seeds are required to satisfy, then could you classify a priori, without having to go to the generalized KLT or generalized CK duality approach? Could you classify a priori on what's the most general ansatz for a CK dual EFT?
Yeah, exactly. That's the point. So right now, these seeds allow to generate really many effective theories. But because we don't know if we have to include poles in there, we don't know if what we generate in this way is everything. That's true. One other thing that I should note is that it's quite difficult to include polarization factors in these seeds, because what they guarantee is that you have the right functional properties, in the sense of cyclicity implies that you get your adjoint structures and all that. To have gauge invariance implied is not so direct, so that requires something else that I haven't discussed. So this is one part that. So yeah.
I see. And are there any computational advantages to using seeds rather than solving for a generalized KLT directly, for example? Are the seeds simpler to calculate because there are fewer of them?
So to be honest, I wouldn't know how to solve otherwise. So otherwise, I think the only way to do it is a bootstrap, or to write an ansatz and to do a bootstrap. But the seeds really, as I try to convey a little bit, they can really be generated and constructed and sort of immediately written down, and also immediately written down everything that's independent. While otherwise you would have to go through an ansatz. So yeah, I would say that computationally it's a big advantage to use seeds.
I see. Any other questions from the audience? Okay, great. Otherwise, once again, let me thank the speaker.